So we've done the intro to calculus, and fundamentally you now understand calculus. Now we begin the advanced study where we do fancy calculus. And we start with that thing that I told you to ignore ages ago, but now we're going to do limits. The limit is a special mathematical tool to calculate the value of a function when we can't calculate the value of a function. Let's say that I have x over x. This is f of x. A number divided by itself is 1. This always equals 1, right? It equals 1 everywhere except x equals 0, because you can't divide by 0. Why? The reason is dividing by 0 in different circumstances gives you different answers. That's why it's undefined. If you have, 1 over x, then it's infinite. That's different than undefined. Undefined means we can't give you an answer because you get different answers depending on what you're doing. But if we actually plot it and use our human intelligence and our intuition, the plot, this is x and f of x, the plot of x over x is just a line at f of x equals 1. It's just a horizontal line, except this one tiny point. And anybody anywhere would look at this, and they would say, okay, it's a horizontal line, but I don't know what it is right at that one exact spot. You know it's going to be 1. You know that 0 over 0 should be 1, at least here. Here it should be 1. But we can't say it is, unless we use a limit. That's what a limit is for. You can use it in situations where you can calculate the value. A limit can be used at any time. But the point is to be able to calculate something that you can't just compute. The notation is thus: limit LIM of something goes to something with a possible modifier, and then all of that is of something equals something. So this here is essentially going to be your function. It doesn't have to be written as a function, but it's going to behave as one. So this might be f of x. We're trying to do f of x equals x over x, and we know everything except x equals 0, f of x equals what? So the thing we're working with is f of x. The thing we're changing is the inputs of the function, in this case x. We're changing x. We're trying to figure out, for this x, what is f of x? Going towards, in this case, 0. So we're taking x and we're going towards 0. We're not actually going to get there, but we're going towards there because we can do this function for any x except 0. We can walk the line either way. So we can move back and forth. We just can't actually reach 0. So we're going towards 0 from anywhere. Just pick a spot, go towards 0. And here you could have a plus, a minus, or nothing. Plus means you're going from the right, from the direction of positive infinity. Minus means you're coming from the direction of negative infinity. And if it's blank, then you're doing both. Or it doesn't matter. You have a plot. Here's your plot. Here's the spot you're interested in. So you have your input, and you start somewhere over here, and you go towards the spot you're interested in. That would be from the right side, from plus. If you start over here and go this way, that's from minus. Or, if it doesn't matter which you do, or you do both, then you just don't put a plus or minus, and you just say 0. And then here is the result, the thing you think you're going to get, which in this case is 1. Why would you want to go from only one side? Well, the plot of 1 over x looks something like this. If you come from the right, you're going to end up this way infinite. If you come from the left, you're going to end up this way infinite because here's 0. So sometimes you have a discontinuous function. It's not well behaved. If you go back to my definition in the first calculus video of what well behaved is, this is not well behaved because it's got an angle. It goes from negative infinity up to infinity. So yeah. So you would have to pick one. But x squared would be a parabola, and you could come from either way. That's why you would go from one side. So, more pretty, limit of f of x as x goes to 0 equals 1, with f of x equals x over x. And you could just write x over x here. Doesn't matter. X over x right there. That's perfectly fine. My green marker is drying out. I lose about a marker a month. It's really annoying. So this is the idea of a limit. We can't actually calculate something, so we calculate values near it, and near and near and near. And we estimate, because we can see this. Our human brain can figure out what that's going to be. If we have this, we can figure out what that is. It's like the pattern of 1, 2, 4, 8. What's the next number in the sequence? It's the same thing. It's a mathematical way of doing that. You can have infinity. If you say the limit of 1 over x as x goes to infinity. So for the positive, the plot of 1 over x is this. If you let x get infinitely big, then 1 over x is going to get infinitely small. So this line actually appears to go to 0. It never does. It never actually does because 1 divided by any positive number, however big, is greater than 0. But it gets so close to 0, it may as well be 0, according to us looking at the plot. This is what it means to go towards positive or negative infinity. Instead of going towards a spot, we just go forever and ever and ever, and we say, what happens if we just keep going? And then the final piece of the notation would be this. If we say this equals infinity, so once again the plot is like this. And it appears, if we go from the right, that 1 over x goes towards infinity because we are dividing by a smaller and smaller and smaller number, which means this gets bigger and bigger and bigger. So the closer you get to 0, the further higher you go. But, we never actually reach 0, but you can get as high as you want just by getting as close as you want to 0 with x. Be careful of this equals. Infinity is not a number, infinity is a notation. Equals infinity means is infinite. It doesn't mean equals infinity, it means is infinite. This is just how we write it. So anyway, that's the notation. A limit can converge or diverge. When you say the limit equals whatever. If you can put something there that's a number, just a number, the limit is said to converge. Converge as in squeeze in. You take the limit, you squeeze in, and you have a number. It's this. If you can't, it's said to diverge, but it can diverge 2 different ways. It can either go infinite, it can just go off into the wild blue yonder and never come back, or it could simply never settle. It could oscillate, it could be noise, and never actually just stop long enough for you to say it's this. So let's do the limit of f of x as x goes to infinity of f of x equals sine of x. This is just the sine wave. Do 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 do. The sine wave will go forever. It will never stop. It'll hit 1, -1, 0, 0.2, -0.3. It'll keep going and going. But as you go further and further and further towards x being as big as you want, it's never going to stop. You can never say it's this, because wait a second, it'll be this. This is a divergent limit in a way that you can't even just say equals infinity. It equals nothing, nothing, nothing. You literally have no notation. You can't do it. This is what I consider truly diverging, because it never settles. But let's make a small modification. Let's say sine of x plus x. So we have our sine wave. Here's the axis. We start out just like normal. We have our sine wave, but then it kind of just runs off into the distance. The sine wave ever only goes to positive or -1. But if we add a number that's positive and growing infinitely big, we're just shifting the thing up. It's still oscillating. It's still oscillating all the way up. But I would still say this equals infinity. It diverges to infinity. It doesn't have no answer. It does reach infinity. Quote unquote reach infinity, you know what I mean. The reason for that is this. Pick a spot right there. This spot. I can then follow this graph, let's say to here, and I can say every single point from here on is bigger than this, no matter what. I can pick another spot. Okay, from there I can go up to here. Every single point from here on is bigger than this spot I picked. And I can do that anywhere. So no matter what spot I pick, even if it's going up and down technically, I can still say if I go far enough, it will always get bigger. Every single point will be bigger from here. So this is why we can say it diverges to infinity. But generally speaking, diverging limits are not useful. They're useful to say, oh, it diverges. But usually we actually want an answer. So how do we make a converging limit here? So let's do something new. Let's go back to our good old standard 1 over x. The plot of which, like I said before, goes infinitely close to 0. It never, ever reaches 0. But if I pick a spot and I say from here on, forever and ever and ever, if I go to here, every single spot is smaller than that spot. If I pick a spot here, I can go down here and say every single spot is lower. In fact, technically you could just, go infinitesimally far, and every spot is lower because it's 1 over x. 0. The limit is 0. We never actually compute f of x at x equals infinity. That's not a thing. This number 0 is never computed, and yet the limit is 0, because you can get as close to 0 as you ever want, no matter what spot you're at. If you want to be closer, get closer. You want to be closer? Get closer. You can get infinitely close. It's meaningless, the fact that you're technically not getting there, because you can still get closer, no matter how close you want to be. That's the idea of a limit. It is functionally that value, even if it never technically is that value, because you can always get closer. No matter what calculation you're doing, whatever precision you're working to, it doesn't matter. You can just get closer, and it'll work as if it was that value. That's the limit. Now it's time for a formal definition. There are multiple of these that all work just fine, but this is the one I find easiest to understand. Let's say you have a plot, and you have a function. and you want to know the limit here. Let's say this is a number c, which means whatever this would be is effectively f of c. But let's say for whatever reason we can't just plug c in and see what we get. So we calculate the limit of f of x as x goes to c. We want to figure out what f of c would be if we could actually just plug c in when we can't. Equals, we'll just say L. F of c equals L, L for limit, so we don't have to keep writing f of c because that implies we're actually calculating f of c. Let's just write L. So what you have is two numbers. Let's say we have epsilon, and let's say we have delta. Both of these are greater than 0. These are just numbers that are greater than 0. Doesn't matter what they are, big or small. Epsilon and delta. If you look at c, and we go here and here, we have c minus delta and c plus delta. So this is sort of a range on the x-axis. For the f of x-axis, we have something similar. Let me just change this to, say, L. And then over here, we have our epsilon. So this is L minus epsilon, and this is L plus epsilon. So what these are doing is they're forming two ranges, and this is the area that we are interested in. Basically, it's setting precision. What we're doing here is we're saying, we predict that L is the value. Epsilon is our error. Let's say we want to be accurate to within 1 millimeter. So epsilon might be 0.001. Plus or minus 1 millimeter. So we say we want to say we're accurate to within 1 millimeter. If the limit is true, if it's correct, then we can find a delta sufficiently close. We might have to go really, really close. This is the detail to which we calculate. But there will be a delta distance from C, from the input where we're trying to get the value. We're trying to figure out what f of c should be. So we go a maximum distance from c. And if we do that, every single point we calculate, f of x of every single point in here of the function is within this range. And you can see here, this is that spot, and it's true. We can calculate every single f of c except at c. So what we say is every single x value in this range from minus delta to plus delta, except for c itself, we calculate. And it must be within what we say is the limit plus or minus the precision we chose. This is the best definition of the limit I have found, the easiest to understand, where you're just choosing precision. So if you're calculating the limit of f of x as x goes to c equals L. C is a finite number. We're not going to one of the infinities. We're going towards a value. We're not doing plus or minus c. We're not going from just one direction. We're going from both. Keep it simple. And this is a finite value. We're not saying it diverges. We're saying this is a convergent limit, a nice, sane limit. There is a specific value that f of c should be, and that's L. So we choose an epsilon greater than 0. This is how close we want to get to the limit. No matter what it is, no matter how small, as long as it's not 0. Because we don't actually get to f of c. We're going to say we can get as close as we want, but not exactly on it. So what is the maximum error from L we're allowing ourselves? So we pick epsilon, and then the definition says there is a delta greater than 0. We pick epsilon, and then there is a delta. If this is correct, if it's not correct, if what I'm saying does not turn out to be true, then the limit is wrong. This is wrong, delete it. We're assuming that this is correct. We're assuming you have done your math correctly. If you have done your math correctly, then for any epsilon greater than 0, there will be a delta greater than 0, such that 0 is less than the absolute value of c minus x is less than or equal to delta. The absolute value of c minus x is just how far x is from c. If this is c, then x is here, it's this distance. If x is here, it's this distance. This is the distance you are from c. The delta is a boundary on that distance. This is saying you must be less than or equal to this far from c when you've got your particular x, but not actually at c. It's not 0. C minus x must not be 0 because we can't calculate. That's the whole point. We can't just say f of c. If we could, we'd be done. We wouldn't need the limit. So for every single x that is delta close or closer to c, except 0, for all of these points, the following is true. The absolute value of L minus f of x is less than or equal to epsilon. Epsilon is the maximum distance we have allowed ourselves to be wrong. Our L, that we have said this is the limit, f of x, which is the actual function value, once again, just like here, this is the distance. If you have your L here, then you've got L plus epsilon and L minus epsilon, and it must be in there. So for every single x other than 0 that's within range of c by delta must generate a function value that is within range of the limit we say by epsilon. If this is not true, then this is wrong. Delete it and do it again. For this to be true, this must be true. Pick a precision for the result. Then there must be a precision for the input, the measurement, that you use to calculate, such that anything within that precision will yield something with that result precision. It sounds like it's a little backwards, but it's really not. It's just saying, here's the thing, if it's false, you're wrong. That's just the way it's worded. And I think I've belabored the point enough for now. You can redo this math a little bit to account for when like x goes to infinity, or when your limit is infinite, is diverging but not oscillating. But let's not get overcomplicated here. I can always do another video if the topic comes up in the future. And this marker is drying out as well. It's a good thing they're cheap enough to just keep buying and throwing away. I would love to buy better markers, but I can't find any. So one more thing to go over is just some basic intuitive rules. If you have the limit of a plus b, so you're just taking a limit, x goes to c equals whatever, of a plus b. This is the same as the same limit of a plus the limit of b. Think about it intuitively. At every single moment, you're adding a and b. And as you take the limit, as x gets closer to c, a is getting close to something and b is getting close to something, which means the sum is getting close to something. If you complete calculating this limit, you're going to get whatever a plus b is. If you complete the limit, you know what a becomes, you know what b becomes. Whether you add them after or before doesn't matter, once you have reached the precision you want. If we're subtracting, it's the same thing. Equals limit of a minus limit of b. Same thing. If you complete the limit, you're going to get a value for a and a value for b. If you subtract them at that point, there's no difference than subtracting them before but reducing their error. If the result of the subtraction is becoming more and more accurate, I'm sure there's some fancy PhD way to prove this, but I'm really not going to bother. This is just straight intuitive. Hopefully. The limit of a constant. For example, the limit of 3 as x goes to 7. When x is 1, this is 3. When x is negative 4, this is 3. When x is 8, this is 3. It's always 3. The limit of a constant is just that constant, because the constant isn't changing. The limit of a constant times something equals the constant times the limit of something. Once again, the constant isn't changing. If you multiply a constant by a number that's getting more and more accurate, it's the same thing as multiplying that number by the final result. The point of the limit is you just reduce the error until the error is 0. So it's the same operation. It's just written differently. But c is always perfect. You can take c out of the limit because it's always perfect. X is not, so you still have to take the limit. And finally, for any other basic rule like limit of a times b equals limit of a times limit of b, you should see a theme to all these rules. All you need to remember is that you are reducing the error effectively to 0. A times b is going to be wrong, and less wrong, and less wrong, and less wrong. Eventually, it's going to be a times b. So if you reduce the error on b to 0, and reduce the error on b to 0, and then multiply them, it's the same thing as multiplying them and then reducing the error of that multiplication to 0. The error is 0, the error is 0, the error no longer sounds like a real word, and it's the same thing. That's all these limit rules. All these fancy limit rules are saying is that it doesn't matter whether you take the limit first or do the thing first. Once you reduce the error to 0, it's exactly the same thing, and essentially the limit fades away. Limit of f of x as x goes to c equals L. Once you calculate the limit, it's just L. So if you have another limit that's m, the limit of f of x goes to L, the limit of g of x goes to m, L times m is just the same as multiplying the limits. Exactly the same thing. So limits, if you see limits and you're trying to solve them and make them simpler, it's as easy as simple arithmetic, as simple algebra. You can join them and split them with no trouble. So finally, just in case this is not clear yet, I'm going to give one final description to try and give a bit more intuition to this. So let's say the limit of f of x as x goes to c equals L. We never get to c. We never calculate c, we never say it exactly is this. We say the limit is this, and then we act as if that's the answer. And it feels like we're taking this weird leap. We're never actually calculating f of c, but then we act as if we know what f of c is, as if we had calculated it. Aren't we just cheating? Here's the thing. Let's say we could calculate f of c and it equals L. That's what we want. That's what we're saying. But you say, no, it equals m. M is not L. Whatever m is, it's not L. You say f of c is actually m. Remember that whole epsilon and delta thing? Where if I want to increase the precision of the result, get closer to L, I can always get closer to c with x. I can always just narrow and narrow and narrow and get closer to c without touching to get closer and closer to L with my f of x. If that's not true, if I can't do that, then I am wrong. That's the whole point of that definition. If I have calculated L correctly, then I can do that. And you can prove limits are true. There's rules. They've done it. But the point is, what if you say it's not? What if you say I'm wrong and it's m? Well, m is not equal to L, which means there is something between L and m. If L is 3 and m is 2, then 2.5 is closer to L than m is. The idea is, here's my function, here's my spot. This is c, this is L. And you say I'm actually wrong and it's this and this is m. So I can have my delta range, my range here that's based on delta. And I can pick an epsilon that gives me a range between L and m. So here is my epsilon range. If I've done the limit correctly and that whole thing stands, all I have to do is pick an epsilon small enough that it fits between L and m. And there will be a delta that I can narrow it into so that the value is in that epsilon. So no matter what m you say, I can always get closer. I can narrow in and blow right past m and say, I still haven't reached L, but I've gotten closer to L than your m is. So I'm still saying my L is true, which you may or may not believe, but your m is definitely wrong, because I'm closer to it. I have proven that every single value of the function close enough is closer to L than m is. So m is definitely wrong. So then you pick an m that's inside the epsilon I just picked. Whatever this precision range is, you say, well, fine, buddy, here. I'm going to pick an m that's inside that range you just picked. I'm going to say, you're still wrong. Well, I can make epsilon smaller. I can make it smaller and smaller and smaller, because it doesn't matter. There's an infinite number of numbers between two numbers that are not the same. You can always pick one between. You can take their average, you get the point between. You can get infinitely small. There's always a number between two numbers, no matter what. So no matter how many m's you pick, I can always shrink epsilon to leave m outside and say, nope, your m is wrong. And you pick an m inside that epsilon and I shrink epsilon again. And I can do that forever and ever and ever and ever, no matter what m you choose. No matter what m you choose, I can still shrink and leave m outside and get closer to L than your m ever is. The only time that's not true is when m equals L. This is what I hope is the final intuition for this. For every single number except L, I can always leave m in the dust on the doorstep outside by just getting more accurate, by adding more decimal points to my calculation. And I can do that forever until the end of time and beyond for any m that is not L. That's why we can act as if this is true. That's why we can say f of x equals L, even if we can't calculate it. We can use the limit to calculate it, and if we do it right, and mathematicians and peer-reviewed papers have proven, we make sure we go through the process and we're not making a mistake. If we make no mistakes, we calculate the limit, and then from that point on, f of x is L. That's the limit, that's the power. To calculate the uncalculatable, the incalculable. And this is why 0 over 0 is undefined. Because depending on what you're doing, you can get different answers for what 0 over 0 is when you take the limit. In another video, I'm going to use limits to do calculus, to calculate the derivative, to calculate the definite integral. The idea behind that is that we can end up getting an exact answer if the math works out. If it doesn't work out, then, we got pies and stuff all over the place maybe. Maybe we'll have to do it by hand and use that successive approximation I just went over. But if we get something nice, we might be able to just write it out as an arithmetic value. So that'll be cool. So until then, I'll be seeing you.